basically, the reason why we would like to talk about sample and interpolation, because at the end of the day, our goal is to process images by means of digital computers, right? And if we need to process an image by the means of a digital computer, we need somehow to represent it in a discrete format, okay? And the process that does that is sampling, okay? So I'm cheating a little bit. So in real systems, you discretize two parts, basically two axes, so to say, of the image, right? One of them is the spatial domain. So an image is a function from RD to R, okay? From R2 to R, let's say. It has two, it has the domain and the codomain, right? The domain and the range. So one necessity in order to be able to process an image by means of a digital computer is to discretize the domain. Instead of having a continuous coordinate, you have a discrete coordinate. You have pixel index ij, right? Otherwise, you cannot represent a continuous object by a computer. Another part of the image that has to be discretized as well is the codomain, is the range. You cannot store infinitely precise numbers in a computer. You need to quantize them, right? You need to represent them by some maybe very high but finite discrete number of representation levels, okay? And this process is called quantization. We are not going to talk about quantization, okay? So basically, in real imaging systems, sampling is always accompanied by quantization, okay? But we will think of an image acquired with a sufficiently fine-grained quantization, so we won't bother too much about this. However, when we will talk about estimation problems, about inverse problems, we can think of quantization as some kind of noise that corrupts the image. Okay, so basically, if you model quantization as noise, this is a pretty faithful model even for coarse quantization settings. Okay, so basically, we'll somehow throw it in through these kind of noise models. Okay, so I will need to show you two technical things before we actually talk about sampling. So basically, two topics from algebra or functional analysis that I'm sure you know, but we'll just align. So one topic you certainly know, another one I'm sure I will define something that you know in a slightly more correct and rigorous way. Okay, so first of all, let me define the notion of an adjoint operator. Okay, so let's say we have two spaces, U and V, two inner product spaces, two Hilbert spaces, U and V, and I have two operators, A mapping from U to V, and B mapping from V to U. Okay? And then suppose I have the following relation holding for every U and V. So I take a vector U in U, and I transform it by A. So the result is a vector in V, right? And I compute the inner product of this image of U under A with another vector V. Okay, so I have a number. Okay, then I do the following. Then I take a vector in U, some arbitrary vector in U, and an arbitrary vector in V. I transform that vector in V by means of the operator B, which maps it to the space U, and I compute the inner product between these two vectors in the space U. Okay, and I get another number. And suppose I have identity between these two numbers for every U and V. Okay, if this is indeed the case, I will say that B, the operator B, is the adjoint of the operator A, and I will define it by A star. Okay, A adjoint, and of course, A is the adjoint of B. Okay, so if you want the visualization, I have the space U. I take a vector U in this space. I have a space V. I take a vector V in that space. I map U to AU. I map V to BV. Okay, and then I compute the inner product here, which will be basically this projection, and I compute the inner product here, which will be this projection. Okay, and basically these two projections have to coincide for every choice of U and V. Then A and B are pairs of operator, and it's adjoint. Okay, and because we are dealing with mostly with real valued functions, I really hate to distinguish between what is called the what is called the adjoint and the transpose. So the transpose operator, A transpose, is the complex conjugate of A adjoint. So for real valued functions, it doesn't make any difference, of course. But since we have eminently complex valued function, the Fourier transform, that we would like sometimes to apply adjoints to, we need to be careful about complex valued settings. Okay. So basically, what does this resemble? You can clearly see here an analogy to a matrix transpose, right? So let me think about let's say an n-dimensional Euclidean space. U and V are n-dimensional vectors in the Euclidean space. A is an n by n matrix, or it can be n by m matrix, doesn't matter. U and V might have different dimensions. Okay, so I can write this inner product like this. Again, it's a real valued space, so I don't bother about writing complex conjugation. And I can take this part and write it like this. Okay? And what is written here is an inner product between U and A transpose V. Okay? And this holds for every U and V, right? So basically you can realize that what is written here and here is an operator and it's a joint, right? A matrix is just an operator on finite dimensional spaces. So basically the adjoint is essentially a more general notion of a matrix transpose. And it has to be a Hermitian transpose conjugated in case of complex valued matrices. And again, the transpose operator would correspond to the regular matrix transpose. Okay. Now we say that an operator is self-adjoint. Obviously, if it's adjoint equals to the operator itself. What would be the matrix analogy? It would be a symmetric matrix, right? Or a conjugate symmetric matrix if we have complex values. Okay. Now, what is the relation between the adjoint and an inverse? So you see, we had operators A from U to V, B from V to U, right? It suspiciously looks like an operator and its inverse, right? At least the domain and the codomain are switched between A and B. So what is the relation between A adjoint and A inverse? Well, in general, there is no connection between adjoint and inverse. In fact, like in this matrix case, the dimensions of the A doesn't need to be a square matrix, might not be invertible at all, right? So there is no relation between adjoints and inverses, except one egregious case. So when indeed we have the adjoint equal to the inverse, of course, this necessarily means that the number of dimensions in U and V must be the same, right? Otherwise, the inverse simply doesn't exist. In this case, we say that the operator is unitary. Okay, and the matrix analogy would be a unitary matrix, or if you want to restrict the discussion to real valued matrices, it would be a rotation or a generalized rotation matrix, rotation and reflection matrix. Okay, so in a generalized rotation matrix doesn't change length, right? So you can clearly see it here. So if I take AU and AV for some arbitrary vectors U and V in the space V, okay? I compute this inner product on V between AU and AV. I can write it like this. So I move A here with the adjoint, okay? And what is A adjoint A? We just said that for a unitary operator, A adjoint is A inverse, right? So this is identity. This is the identity map, okay? So basically what I have is that this equals to UV, okay? So basically you have your space U, you have your space V, you have two vectors here, U and V, and these are their images under the unitary operator A. Okay, so when you measure inner products here, and inner products, of course, induce norms and lengths, basically it means that unitary operators don't change lengths, they don't change angles. Okay, and this is what a rotation operation does. So it's an isometry on these two spaces. Okay, questions? Okay, so let's see, just as an exercise, let's see adjoints for some common operations that we already discussed, and we'll need them for the sequel. Okay, so let's take the translation operation. The translation operation that takes fx and maps it to fx minus p. P is some fixed vector in Rd. It's the amount and the direction by which we translate. Okay, and let's compute its adjoint. How do we compute the adjoint? We compute an inner product between this translation and some arbitrary functions f and g. Okay, so this should hold for any f and g. We'll just pick two arbitrary f and g and fix them. Okay, and now let's compute the inner product. So we'll just write the inner product integral. Instead of tau pf, I'm writing directly this term, right? This is the shifted version of f at point x, okay? And I'm doing inner product with g. Well, let's change coordinates. I will write x prime as x minus p, okay? Because I want the operator to appear on the in the second argument of the inner product. Dx, of course, remains the same. It's just translation. So I'm getting this, okay? Sorry, and this is nothing but what is written here. It's x prime minus p, right? So I'm writing it in this form because what is written here is tau minus p g star evaluated at point x prime, right? So I can write that this equals to the inner product between f and tau minus p g. This is true for every f and g, right? So you can see that this operator tau p and this operator tau minus p are the adjoint of the other, okay? Because this is the definition of the adjoint. Okay, so we have this. Now, because we don't have any complex values here, right? Because we are not messing up with f itself, but just with the translation. If I compute the transpose of this operator, it will be exactly the same. So the transpose of this operator would be the complex conjugate of the adjoint. It's exactly the same. Yes, a question? Let me write it here. Okay, so the adjoint is defined this way. The adjoint is defined this way. I would like the inner product of AU V. Let me write it. Let me write it in our terms of f and g. Okay, if you allow. So it's the inner product of A f with g, and I'm not specifying the space. Of course, it will be L squared on Rd, right? The space where f and g belong to. And this has to be equal to f inner product with A adjoint g, obviously for every f and g. Okay, this is the definition of the adjoint. Okay, tau minus p is the definition is the adjoint of tau p. Okay. Let's have a look at another operator. So basically, what we had tau p was a domain transformation, right? It transformed the coordinates of the function. So we had a more sophisticated domain transformation by means of a regular matrix A. We call it stretching. Okay, it's the most general setting. A particular case when A is a diagonal operation, it would be called scaling, some non-uniform scaling. If A is a scaled identity matrix, it would be uniform scaling, right? And if A is a rotation matrix, it would be called rotation. So basically, all these particular cases are basically setting some specific algebraic form of the matrix A in this general stretching operator. Okay, so let's compute the adjoint of this stretching. Okay, so again, I take two functions f and g and compute the inner product between SA, f, and g. So I write this integral, as you can guess. What will be my next step? Coordinate transformation, right? I would like to replace this with a new name. Let's call x prime to be ax, right? But now I have a scaling that is applied to the volume element, right? So some scale has to appear, right? And this is the scale that appears. This is the determinant of the Jacobian of the transformation, which is the same at every point in the volume. I write now f with the argument x prime, and I put the inverse of a in this argument of g. Okay, and again I assume that a is regular, so a inverse exists. Okay, so let's write it like this. It is the inner product. What is written here? It's the inner product of f with this operator acting on g. So it's the scaling by a inverse. So it's the stretching by a inverse, and also scaling of the function by the inverse of the determinant of a. Okay, and we'll see this scaling further when we talk about sampling on general lattices. A is a d by d regular matrix. It can be anything, but it must be invertible. Otherwise, it's not a coordinate transformation. Okay. So this is our stretching. Let's just write it in a nice operator form. The adjoint of SA is SA inverse scaled by the inverse determinant of A. Okay? By the volume of, basically inversely scaled by the volume of the transformation. Okay? And of course, again here, the transpose will be equal to the adjoint. Any questions? Next. What happens if we have a convolution? So we have the action of a Topless operator, of a linear shift invariant operation, with some kernel, some impulse response function h. What will be the adjoint of a convolution? What is inverse convolution? First of all, adjoint is not inverse, right? So what is? It's not inverse convolution, right? So let's first do the math and then see pictorially why it is like this. Okay. So let's first do the math. It's quite straightforward, right? So I write the action of this operator on f as h convolution f. Compute the inner product. So here I have the inner product. What is written here is just this, right? Just the substitution of the convolution. I'm evaluating it at point x. The convolution variable, integration variable is x prime, and then the inner product is integrated over the variable x. Okay. Let's shuffle the integrands in slightly different order. So I will first integrate over x, and then I integrate over dx. So basically, I push x here inside because h is a function of both x and x prime, right? And then I will put the complex conjugate over h. I will remove the complex conjugate over g, and I will put it here. Okay, so didn't change anything. But basically, what you see here. So what is this? What is this exactly? Well, so in order for it to be convolution, I need minus x to appear under h, and here it appears plus x, right? So it's not convolution with h adjoint. It's convolution with h adjoint with a mirrored domain, right? So let me define this h bar. H bar of x will be h minus x. Okay. So basically, I'm just reflecting it about the origin. So every coordinate gets reflected. And we can write it like this, right? Compactly. So basically, we can say that the adjoint of convolution with h is convolution with h reflected and complex conjugated, or if we want the transpose operator, it will be just convolution with the reflected impulse response function. Okay. So now, why does this make sense? Let's see a discrete one-dimensional example. So we said that applying convolution with h is basically like multiplying by a matrix h, right? So a matrix h, a Topless operator, will look like this. We'll have h0 here. I'm writing it in the discrete setting. So just think of a continuous matrix. If it is in the continuous setting, I will have h minus 1 here, h plus 1 here, h plus 2 here, h minus 2 here. So what I'm denoting here, it's a topless matrix, and what I'm writing are the values of the diagonal. Okay, so these are the values in terms of the impulse response function, right? Now, what happens when I compute the adjoint? What is the adjoint? It's the transpose of this matrix, right? What happens if we transpose this matrix? Will it remain topless? It doesn't mean to be symmetric, but it will still remain topless, right? It will have, again, this diagonal structure. But the diagonals will be flipped, right? What you will have, once you transpose, this will become plus 2. This will become plus 1. This will become minus 1. This will become minus 2, right? So this would correspond to convolution with a mirrored h. Can you see it? Okay. So this is basically a visualization of why our math was correct. Okay. Any questions? And again, the transpose will be exactly the same without the complex conjugate. Sure. The slide just got erased. Unfortunately, it is not persistent. But basically, what I'm saying is that if you think of convolution as a multiplication by a topless matrix, where the diagonals will be assuming the values of the impulse response function, if you compute the adjoint, it is like computing the matrix transpose of that matrix, right? So the diagonals above the main diagonal will go below the main diagonal, and the diagonals below the main diagonal will go above. So the diagonals above correspond to the negative samples of the impulse response. They will now become positive samples of the impulse response, and vice versa, right? So this is like taking the impulse response and reflecting it on this one-dimensional axis. So in multiple dimensions, it is the same. Instead of having a topless operator, you will have a block topless structure, but the reflection will also hold. Okay, and this is basically what we did here with these integrals. Any other questions? Okay, so let's see another operator, a very trivial one, pointwise product. Okay. And you will see why I am insisting on doing all this exercise very briefly. So let's have a pointwise product. I have some fixed function h, and I'm doing a pointwise product of h with f, inner product with g. Obviously, it goes like this. I move h here. It is a special case. You can think of element-wise product. Well, so okay. So I basically so in the discrete domain, in case of matrices, you are absolutely right. You just put an impulse response that has one central sample non-zero, and the rest is zero. And you have a diagonal matrix. It's a particular case of a topless matrix. In the continuous case, this is not the case. What is the meaning of a diagonal, right? So you need to define what we will do next. We need to define a particular kind of a function, which is not a function, that we will call it delta. Okay, and with the delta, you can do exactly what you said. Okay, this is the analogy. I'm just moving h here to g, right? Some bug here. I don't know why those equations appear. I will fix them. So basically, I'm moving h here, right? I'm doing complex conjugate of this h, right? So I'm writing it like this: Rd of f x h conjugate g x everything conjugate dx. Okay, and this is nothing but the inner product of f with h complex conjugate pointwise product with g. Okay, so basically the adjoint of pointwise product is pointwise product with the complex conjugate of the function. And if you want to compute the transpose, it will be just pointwise scaling with exactly the same function, without the complex conjugate. Okay. Okay, let's see what is the adjoint operator of the Fourier transform. I remind you that this is how our Fourier transform is defined. Let's compute the adjoint, and I will write the second function g in the second argument of the inner product as g capital because it's just notational convenience. I will because we denote by capital letters the functions in the Fourier domain, and I will denote its argument as xi and not x. But it's just an arbitrary notation that I decided to choose just to avoid confusion. Okay, so let's compute this inner product. This is the inner product. I have the Fourier transform evaluated at point xi. I have g conjugate evaluated at point xi. I integrate over xi. This is my inner product, right? It's also inner product on L squared RD. So now I substitute the definition of the Fourier transform here. This is what I get, right? So the Fourier transform goes over x. The inner product goes over xi. Let's just change the order of integration and reinterpret the integrands differently. So what I will write the inner integral will be over xi. I will remove the complex conjugate over g, and I will complex conjugate the exponential, so hence the plus sign here, and I will keep the conjugate here. Okay, so this doesn't change anything. Okay, the arguments, the angles of these complex variables remain the same. But now I can interpret what is written here as the inverse Fourier transform of g, right? And what is written here is the inner product between f and the inverse Fourier transform of g, right? This is what is written here. So I can summarize this by saying that the the adjoint of the Fourier transform is the inverse Fourier transform, which means in our definition that the Fourier transform is a unitary operator, okay? And unitary operator means that it is an isometry. It preserves length, preserves inner products, okay? And from this property, we can immediately derive the following identity. So if I take two functions f and g in the original domain and compute their inner product, it will be equal to the inner product of their Fourier transforms, right? And this is called Plancherel's identity. Yep. F and g, thanks. Of course, it's f and g. Okay, thanks. And then I can substitute the particular case if f equals g. So basically, this will be my identity, and I can interpret the inner product of f with itself as the L squared, L2 norm squared, and L2 norm squared here as well. So basically, it means that the Euclidean length of a function in the space domain equals to the Euclidean length of its Fourier transform, and this is known as Parseval's identity. Okay? It's just the consequence of the Fourier transform being a unitary transformation. Questions? Okay, so I would like to remind you about one prominent fact that basically became increasingly important once math transitioned more or less from the Riemannian formulation of integration to Lebesgue's formulation of integration. When you write integrals, when you write an integral, let's say with a function fx dx, and maybe there is something else here. If I give you two functions looking like this, one of them is the orange function f, and another one is the blue function g. So they only differ at a small set of points. Okay, so the point-wise, these are not the same functions, right? But if I'm now telling you that the set of functions on which the functions differ point-wise has measure 0, basically it happens with 0 probability, if you will, can you distinguish between them by means of integration? No, right? So basically all these are the same functions if you integrate with respect to them. And basically, because many of our operations involve inner products, right? We work with inner products. We don't really care about the point-wise definition of our functions. So basically, we can think of some equivalence class of functions that may be different up to a measure 0 set. Okay, so then thinking of an object that is a function becomes inconvenient, and we would rather think of some kind of an equivalence class of functions. And for that, we would like to define what is called a weak form. It's exactly this equivalence class. So the way we define weak form, I will take some test function, some function that will denote as psi, a test function. It can be real valued, it can be complex valued. I'm ignoring some technical details. It has to be sufficiently well behaved. Okay, so for example, it has to be, let's say, it has to be sufficiently smooth. It has to decay sufficiently fast when x goes to infinity. Okay, but these are again technical details that will not arise in our elementary derivations that we have in the sequel. And then I will define an inner product of f with this psi. And basically, just as a very annoying point, in the Hilbert space theory, we define inner products with the complex conjugate. And in distribution theory that deals with these kind of weak forms, we define inner products without the complex conjugate. So that's annoying, but this is how it is. And I will show you exactly when we define the delta why we want it without the conjugate. Okay? Otherwise, we won't have all the nice properties that deltas and other distributions have. Okay, so just a strange definition. We are defining the inner product with the test function conjugated rather than the test function itself. And usually the test function will be a real valued function, so we don't care about this complex conjugate. But if we do happen to take a complex valued function there, then this conjugate is important. Okay. So let's do the break, and we'll see how this helps us to define sampling. Okay, let's continue. So we defined this weird way of looking at functions through their weak forms. So again, a probability metaphor here would be probably in place. So imagine you have some density f, and I insist on not specifying the probability density, because again, density it's an equivalent class. If I define you a density that differs from another density point-wise on a set of 0 measure, you will not be able to distinguish between these two functions in terms of anything that has probabilistic outcome. I will rather define you this density through moments. So I will give you all the possible moments of this probability distribution, and you can unambiguously reconstruct the law of probability or the equivalence class of density function that underlies it from the moments, right? And what is written here is just a moment of this density function, right? So what you can if you interpret f as a density, as a probability density, this is just an expectation of psi under that probability distribution, right? Which is a moment of the distribution. Okay. And you can define in weak form not only functions, of course, but also measures. So again, think of a probability measure. By looking at its moments, you define a weak form of a probability measure. So basically, weak form can be thought of as some kind of a expression, an expression of this equivalence class of functions or densities or probability distributions or other mathematical objects. Okay. So I would like to define what is known as generalized functions, or more rigorously distributions, which has some basically has the same name as probability distributions, but these are different mathematical objects. So it's just to add confusion. So basically, in our terminology, a distribution will be a linear functional. So a function is a function of a function that will take a test function and produce a number. Okay. And I'm not going into technical details, but this test function has to be sufficiently well behaved in order for this functional to be defined. Okay. So for example, if I take the finite dimensional case, in Rn, every linear functional can be defined in this way. Okay. So a linear functional in the n-dimensional case is a linear function, right? Because the input object is a vector. It's not a function. Okay, and I'm taking a vector as an argument. I'm producing a scalar value. Okay, so it's a linear function, and you would agree with me that every linear function can be written like this. Okay, with some set of coefficients hi, I from 1 to n, that distinguish between one function and another. Okay, so this is the finite dimensional Euclidean case. Okay, any objections? No objections? It's an inner product. It's called a scalar product, right? It's a dot product. Yeah. So basically, a dot product in the n-dimensional Euclidean case defines every linear functional you can imagine. Okay. So it's not a function. It's a function in the n-dimensional case. Any function you can imagine, any linear function you can imagine, can be written in this form. Okay. If you disagree, show me a function that you cannot write in this form. Yeah, exactly. So there is some confusion between linear functions and affine functions. Affine functions also have an offset, right? But a linear function can be written in this form. Okay. You don't have an example of a linear function that cannot be written in this form. Okay. What happens in the infinitely dimensional case? In the infinitely dimensional case, not every linear functional can be written in this form. Okay? There will be some linear functional for which h is not a function. Okay? And I will show you one egregious example, which will be the delta distribution. Okay, so for delta, you cannot write it in this form. Okay, so we can say that the space of inner products, or in the finite dimensional case, the space of inner products and the space of linear functionals are isomorphic. Basically, they are just the same thing expressed in different terms. And the infinitely dimensional case, this is no more true. There is no isomorphism between the space of linear functionals and the space of inner products. The space of linear functionals is bigger. It has objects that cannot be expressed as inner products with functions. Okay? It's an important point because we are not going to deal with functions anymore when we talk about distributions. This is exactly a way to generalize the notion of a function. Okay? So just because we think of this linear functional as a weak form of a function, I will be using this notation. So basically, again, a distribution L is a functional that takes a test function psi and spits out a number. Okay? So let's just see what happens when my distribution represents a weak form of a function. I will be simply writing f with psi conjugate, right? So this is a weak form of a function f that we have seen before, right? So I can write it, of course, as some distribution f acting on psi. Okay, it's a linear functional, but it's convenient to write it in the form of an inner product. So I will continue writing it as an inner product just as a syntactic sugar for saying that I'm applying a linear functional on psi. This is not an inner product, of course, right? Because L is not a function. It's a different mathematical object. An inner product is not defined on that object. Okay? It would be nonsense to interpret it literally, but we are interpreting it just as a notational convenience. Okay? And you will see that because of interpreting it in this way, we will define a very useful way of transforming distributions. Okay? Any questions? So is it clear? We are just operating with linear functionals on test functions, and we are writing them as if they were inner products. So they can be represented as inner products in some cases, and in some cases they cannot. If we talk about finite dimensional spaces, they can always be represented as inner products. Okay, as we have seen in the previous slide. Yes. Yeah. L is a linear functional. It's a linear function. So it's a function that receives a test function and gives you a number. So it's a functional. Okay. Yes. In the mathematics, it's called a functional. Okay. A functional. A functional is a function of a function. Okay. And we call it distribution. Nothing to do with probability distribution, or at least it's not the same thing. It has to do with probability distributions, but it is not the same object. Okay? Yes? Well, the boldface is just a vector, right? So psi here is a vector in Rn, obviously, right? And H as well. In the finite dimensional Euclidean case, functions are vectors, right? Objects. So basically, let me say it the other way around. So vectors in functional spaces are functions. Okay, vectors in n-dimensional Euclidean spaces are regular vectors, n-dimensional tuples. What do you mean? In Rn, basically our vectors are simply n-dimensional tuples of coordinates, right? Okay, so basically there are no functions in Rn. In Rn you have just finite dimensional vectors, right? Now, if you go to an infinitely dimensional space, an infinitely dimensional space, like a space of functions, doesn't have, so it still has vectors. Algebraically, these are vectors, but these objects are functions. Okay, so you can think of a function as a vector. A space of function with an inner product is a vector space. You can scale functions, you can add them, right? It's a vector space. Okay, so in that vector space, vectors are actually functions. Okay, and we are interested in that kind of spaces. And in that kind of spaces, a linear functional cannot be written as an inner product anymore, or not always can it be written as an inner product. Make sense? And I will show you an example of a function that cannot be written in this way. Okay, so let's just have a look at a particular case of a distribution that can be written as an inner product. So I will denote it by F, and this is a distribution representing, in a weak form, some fixed function F. Okay, I'm fixing some function F, and I'm representing it in a weak form through the inner products of that function with test functions that I'm denoting by psi. Okay, so again, from measuring this, the value of this function on every possible test function, I will never be able to recover F point-wise exactly, but I will be able to recover it, recover one of the functions in that equivalence class. Okay, so I will be able to recover it up to some set of measures 0, right? This is the meaning of a weak form. Okay, so this is my distribution. It's a particular case of possible distributions that I can write. In this case, it can be represented as an inner product with a function. And let's take H to be an operator on the space of functions. So in our language, F is a signal and H is a system. Okay? And I would like to define, or to at least to examine, how H acts on a distribution F. Okay? Of course, H expects a function as an input. If I feed it with L, L is not a function that H expects, right? It's a completely different mathematical object. It's not a function from Rd to R. It's a linear function on the space of functions from Rd to R. It's a completely different mathematical object. So if I feed it to H, H will choke, right? It's not built to digest these objects, right? But still, in this case, there is a very meaningful way of defining it, right? So if I write this HF acting on psi, I can think of it as H transforming F acting inner product with psi conjugate, right? Okay. And of course, I can move H with a joint sign here and write it like this. Okay. So it will be the inner product of F with H adjoint acting on psi adjoint, on psi conjugate, or I can write it like this. It will be H transpose acting on psi adjoint, a conjugate on everything, or I can write it as functional F acting on H transpose acting on psi. again, that's why I restricted my attention to a distribution that represents a function. Okay, so if you just remove this, what is written here is perfectly valid, right? Okay, so if I think of my functional as an inner product, what is written here is perfectly valid. I can act on f with the operator h. I can act on psi with the operator h adjoint. It will give exactly the same result, right? But now I remember that my inner product actually represents a linear functional, so I can write it this way. Okay, so I could write it this way for a functional represented by an inner product with a function. Okay. For a general function, I cannot write it like this anymore, but I can define it like this. Okay? I will just define it this way. I will say that when I write h acting on L, this is just mathematical nonsense, right? Because h cannot take L as an input, but I will extend the action of this operator h to the space of distributions by defining it this way. Okay? I will not apply h directly to L. I will apply h to the test function. I will apply it with the transpose, with the complex conjugate of the adjoint, and then plug it into L. Okay, and this is perfectly legit. Okay, so it's a definition. I can basically, just as a syntactic sugar, I can still write it as HL inner product with psi conjugate, and it makes perfect sense when f is a weak form of a function. When it is not, this is just a definition of what it means to apply an operator to a distribution. Okay, and this, as you will see, this is a very useful and consistent way of transforming distributions. Okay, so basically, when a distribution represents a weak form of a function, it's just transforming a function. Okay, this is what we've seen previously. And when it is not, it defines what it means to transform a distribution beyond that class of linear functions that can be represented by means of inner products with functions. Okay? Is it clear? We'll see examples. So the example that we actually care about is this distribution. We will call it delta. It was introduced by Paul Dirac. And actually, before him, in some not exactly in these ways, it was even defined by Fourier. If you go and read his writings carefully, he actually defines something that looks like a delta, and it's Fourier transform. But basically, the formalism in the form of distributions that I'm showing to you is due to Laurent Schwarz, not the same Schwarz of the Cauchy-Schwarz inequality. So basically, we define this linear functional. We call it delta. The functional takes a test function psi and responds with the value of this psi at point 0. Okay? So this is how our delta distribution is defined. Now, in some sloppy signal processing literature, actually in most sloppy signal processing literature, this thing is called a delta function. Now, so you integrate psi with the delta function and you get this. I argue that there is no function that will give you this when you integrate with it. Okay, there is no function h that can do this. Okay, it has to assume infinite value at 0 and to be zero elsewhere, and to have area under the function to be equal to 1. There are no functions that can do this, right? But we can define this as in a weak form as a distribution. Okay, that's why we need all these formulas. Okay, so again, as a convenient notation, we are going to write the application of this functional to psi as an inner product between delta and psi conjugate. Okay, this is again just a notation. This inner product is not defined because delta is not a function. Okay, but we still will just denote it for convenience. Okay, so this is just sort of a syntactic sugar, just a convenient notation. Now this is not convenient. This is not legal at all, right? There is no such such a function delta that can be integrated with psi to give some meaningful result, because delta is not a function. Okay, so I would like to completely abolish and avoid this kind of notation. It could be convenient, but let's not write it because this is nonsense. Okay. So I would like to show you some properties of this delta distribution. I will refrain from calling it delta function. Sometimes it will slip from my tongue, but correct me. So the general blueprint for studying how different operators act on the delta distribution will be basically through our definition of definition through the transpose operator. So an operator H acting on delta will be delta acting on psi transformed by the transposed operator. Okay, and because the way we define delta, it will be the value of the test function transformed by the transpose operator at point 0. Okay, because this is how delta is defined. Okay, so this is how we are going to basically to study the properties of delta. Let's see what it means to translate delta. So if I apply the delta function translated by tau p to a test function psi, I will write the transpose operator, which is this, right? This is the transpose of tau p applied to the psi function at 0, and this is nothing but psi at p, right? Makes sense? So delta, translated delta, instead of giving me the value of the test function at 0, gives me the value of the test function at p. Okay, next. Pointwise product. If I'm to multiply delta by a function f, and here it must be a function. If it is a distribution, this pointwise product is not well defined. If I have a fixed function f, I do pointwise product with delta. It is taking the adjoint operator or the transpose operator of this pointwise product, which is pointwise product itself adjoint, applying it to the test function and evaluating the result at 0, right? Which is f0 times psi at 0, and psi at 0 is delta psi, right? So basically, when I do element-wise product with the delta, I completely ignore the values of the function everywhere except at 0, and I just scale delta by the value of f at 0. Okay? Makes sense? Now, because of this property, as you probably start seeing, I'm going to use delta as a formalism for sampling. So basically what I did, I sampled the value of f at point 0. Okay, and if I shift the delta, I'm going to sample the value of f at point p. Okay, and ignore all the rest. Okay, so this will be my formalism for sampling. So I can say that f inner product with delta is f0 scaling delta. So remember, delta is a linear function, all right? So scaling basically is scaling inside and scaling outside is the same. I can move the scaling from the argument to scaling of the function itself. Okay. What happens with stretching? So if I apply stretching to the delta, it is akin to applying the transposed stretching to the test function itself. And this was the transpose operator that we derived before, right? It is actually equal to the adjoint. So let's do this evaluation. First of all, I have this scaling by the volume of A, right? And then I substitute A inverse to the argument, and then evaluate the result at 0. And the result will be psi at 0 is just delta psi, scaled by the volume of A. Okay? So stretching the delta is like scaling the delta by the volume of the stretching. Okay? And of course, you know it from the one-dimensional case, right? In one-dimensional case, you remember that we wrote some nonsense of this form, right? This is the correctly notated multi-dimensional case. Okay. rotation. Now, what happens in case of rotation? If you substitute A to be a rotation matrix, so you see basically the stretching of the domain of delta is just scaling by the volume of the stretching. In the case of rotation, the volume of the stretching is 1. So delta is invariant to rotation. Okay, you see, rotating the delta keeps it delta. It's rotation invariant. Rotation and reflection invariant, of course. And because it's rotation invariant, this is the general notion of being even, an even distribution. Okay, symmetric distribution. What about convolution? So convolution with the delta, it will be the action of the transpose operator, and the transpose operator will be convolution with a mirrored impulse response function without the complex conjugate, because transpose doesn't have complex conjugation. This is exactly where the Hilbert space theory deviates from distribution theory. We don't use adjoints, we use transposes. So it will be convolution of the test function with a mirrored impulse response, right? So let's evaluate this convolution. So basically I have here convolution, basically the inner product of convolution with just in my notation, the inner product of convolution of H with delta, inner product with psi. Of course, this is just a way of saying that I'm acting by a shift invariant operator on the distribution delta. And let's write this convolution and evaluate it at 0. This is what we are going to have. Now remember that this H bar is just H at minus the argument, right? So let's write it like this. Let's write it as the integral of psi x hx dx. Okay, and this is nothing but the inner product of H with psi conjugate, right? Now, what is written here is a weak form of the function H, right? What is written here is the action of the delta distribution on the same test function. This is true for every psi, okay? Can you see it? So basically, on one hand, we have, on the left-hand side, we have the action of the delta of this functional that we defined as delta. On the other hand, we have the action of a functional defined by the weak form of H. So we can say that H convolution with delta is H. Okay? Can you see it? Is it clear? So we started with some distribution that cannot be represented by a weak form of a function. This was our delta. We convolved it with H, and we got a distribution that can be represented as an inner product with a function. That function is exactly the same H. Okay? So then we can write H convolution with delta equals H. This is perfectly legit if we interpret it in this way. And it means basically that if we form a group, of functions with the multiplication, with the operation of the group defined as convolution, delta will be the unit element. Okay? Delta will be the unit element. Now, if we used the Hilbert space formalism of inner product, we would have, instead of H convolution delta equals to H conjugate, right? So it wouldn't be a unit element anymore. And this is a very convenient property of the delta. So we want it to be this way. Actually, it's the only unit element that this group might have. Okay, it's unique. Let's see the Fourier transform. Okay, what happens with the Fourier transform? So let's take the Fourier transform of delta. It's of course defined as the transpose of the Fourier transform acting on the test function evaluated at 0. And here I'm writing the test function as psi capital, just because it will be, I will think of it in the Fourier domain. Okay, so what is F transpose? F transpose, I can think of it as F conjugate, F inverse conjugate, right? Because F adjoint is F inverse. F transpose is F adjoint conjugate. So I will write F inverse of psi conjugate on this entire function evaluated at 0. Okay? Make sense? Let's write it explicitly. This is the inverse Fourier transform of psi conjugate, right? Conjugate on the result, evaluated at x equals 0. Okay, so it's an inverse Fourier transform. I'm calling its argument x. It's evaluated at x equals 0. Okay. Now this exponential, when I plug 0 into its argument, is just a constant function equals to 1. Okay, so I will denote this constant function as this bold 1. So it's not a number, it's a function that is constant everywhere, or at least constant everywhere up to a set of measure 0. Of course, we cannot distinguish between such pointwise differences. Okay, so basically this is essentially an inner product between this constant function and psi conjugate, right? So here there is no conjugate, so I need the conjugate in the argument of the inner product, right? Just to keep things consistent. So again, what we had, we started with the transformation, with the transformation of delta by means of the Fourier transform. What we ended up with is a distribution that can be represented by the weak form of a function, and this function is the constant function 1. Okay? So again, as before, we can equate by saying that the Fourier transform takes delta to the constant function 1, and of course the other way around. Okay? So basically, something that has an impulse as its impulse response, something that has a delta as an impulse response, will have white spectrum in the Fourier domain. So basically, all the frequencies will have the same energy. If we now combine this with the translation property, translation becomes modulation in the Fourier domain, right? So a translated delta will simply become, if we translate delta by p, we end up with a harmonic with the parameter minus p in the Fourier domain. Okay? This is just a combination of the property of the Fourier transform with this property of the delta. Okay? Questions? Okay, so now we are coming to, basically all this introduction was to define this object that we have here. And basically, I'm calling it a bed of impulses, or Dirac's bed. It's a very uncomfortable bed if you think of it. It's basically it's made of very very high, infinitely high nails, infinitely thin and infinitely high nails placed on the bed on a regular grid. Okay, so it would be a bed in the two-dimensional case. It will be some high-dimensional bed in the d-dimensional case. So basically, what we have here is just a collection of translated deltas on the integer lattice ZD. Okay. So basically, n is a multi-index. I think I wrote it here. N is a multi-index. It looks like n1 until nd, and every ni is in Z. Okay, is an integer number. So you see, basically, it looks like this in 1D. It looks like this in 2D. I'm using these arrows to indicate deltas, right? Of course, these are not functions, but these are shifted delta distributions. Okay. Now let's look at the properties of these. I'm specifically interested in two properties of this Dirac's bed. I'm denoting it, by the way, denoting it by this symbol because I just don't have enough typesetting skills to make three arrows like this. But I think it's a convenient symbol. Okay, so pointwise product of some fixed function f with this Dirac's bed. Let's just use the properties of the delta that we had plus linearity of this functional, right? So I'm applying translation to f. So it's a sum, of course, over the integer lattice. Translated f, translated scaled, element-wise scaled, point-wise scaled delta applied to the test function psi. I can push the element-wise, the point-wise product to the test function itself. Okay. and push the translation inside the delta as well, with just minus n because of the transpose operation, right? And what I get, basically, if I evaluate delta of this transformed, this translated test function, I will get the sum of fn times psi n, okay? And psi n is nothing but the translated delta of psi, okay? So basically, you started with something that that looked like the translated versions of delta, okay? And you ended up with the same thing with the deltas scaled by the value of the function at that very point n. Okay, so let me just draw it. This is function f, and this is how the Dirac's bed, the one-dimensional Dirac's bed, is going to look like. Okay, so the height of the deltas, or the scale of the deltas, will take the value of the function right here. And what I'm saying that this is a convenient mathematical instrument to represent the action of sampling. Okay, we'll actually see that real sampling is not exactly this. We never take this instantaneous value of the function. We do some integration, but we'll still be able to represent this integration as the action of this thing plus convolution with something. Okay, so this is the pointwise product. What about convolution of a fixed function f with Dirac's bed? Again, let's use linearity and the convolution property of the delta distribution. Okay, so I have shifted I have shifted f convolution with delta acting on test function psi. I'm using the transpose of this convolution operator to push it to the test function. So it's shifted delta acting on the mirrored version of f convolution with psi. Okay, and because of the way the shifted delta is defined, it's the value of the convolution of mirrored f with psi at point n. Okay, this is what shifted delta does to the test function. Okay, let's now write this convolution again. We have basically this integral standing for this term here. It's the convolution of f mirrored with psi. I already mirrored f, so I wrote it in terms of f itself and not f mirrored. That's why the integration variable appears here with plus and not with minus. And I'm evaluating this convolution at point n. Okay? So let's just swap the order of integration and sum. These are all the kind of sloppy things that you can do. You need actually quite serious mathematical machinery to rigorously prove that this is possible, but this is possible. So basically what I have here is the sum over the integer lattice of fx minus n, integral with psi at x dx. Okay? So what you can see here is the inner product. So let me just write it like this. What you can see here is essentially an inner product of psi conjugate with this function. Okay, what is this function? It's a periodized version of f, periodized on the integer lattice, right? And basically, what you are saying that the convolution of f with the Dirac's bed, which is a distribution, equals to a weak form of the periodized version of f. Okay, so you can say that convolution of f with the Dirac's bed is the periodization of f on the integer lattice, on this thing, right? And just a visualization I had here. Here. So you take f that looks like this triangle, you replicate it on the integer lattice. So let's say here it's 0, here it's, let's say, 1, here it's 2, here it's -1, and so on. You replicate it and then you sum. This is what I mean by periodization. Obviously, you can see that this is a periodic function. It is periodic with a period on the integer lattice. It's the d-dimensional analogy of being periodic. Okay. So if you add any integer shift to the argument of this function, you get exactly the same value. This is what is meant by being periodic. So let me just write it down. So periodic, or let's call it z d periodic. It means that fx. So let me write this thing as f tilde at x. It means that f tilde equals to f tilde f x plus n coming from the integer lattice. So by this I mean that my function is periodic. Okay, and I started with a function that is arbitrary. I just periodized it by adding its integer replicas to the function itself. Okay, summing them up. Was there a question? Okay, so basically it's this periodization. Okay, so again, multiplication with Dirac's bed is sampling. Convolution with Dirac's bed is periodization. Okay, so let me show you one result. I have some time. I would like to show you one, in my opinion, astounding fact, not about Fourier transforms, not about deltas. It's an astounding fact about integer numbers, right? So it's a very profound fact. So let's take a test function psi and periodize it. We periodize it by, as we have seen, by convolution with Dirac's bed. Okay, and as a result, we get this psi tilde. Okay, it's periodic, obviously, on 0, 1 to the power d. Okay, because it is periodic on this d-dimensional square. Pardon? No, so it's periodic on this. It means that basically the function, if you look at its level lines, it will look like tiles of this fundamental square, d-dimensional square. Okay, it will be just replicas of this. It will repeat itself in these kind of tiles, right? It's like tiling a floor. No, it will repeat itself infinite number of times in every direction. No, it's not n. So you see, it's zd, right? It's zd. It's 0, 1, 2, 3 raised to the power d. So it's all integer d-dimensional vectors. Okay. So basically, you go in units of 1 in every direction, because these are the elements of this lattice. We'll talk about lattices next week, right? And we'll see basically what is a more general lattice. But basically, this is we are periodic with the period of 1. So just take d equals 1. Periodizing psi x minus 1, psi x plus 1, psi x minus 2, psi x plus 2. Basically, you have a period of 1, right? Makes sense? So because we know that periodic functions can be represented as Fourier series. So Fourier series is just a Fourier transform with discrete spectrum. So it is concentrated in discrete locations in the Fourier space. So we can represent this d-dimensional periodic function as the Fourier series with our famous harmonics and Fourier coefficients Cn that are obtained. So these are explicitly the harmonics, and the Fourier coefficients, because the harmonics form an orthonormal basis, the coefficients are simply obtained by projecting our function that we would like to expand into the Fourier series onto the basis functions, onto the harmonics, right? So it's exactly like the Fourier transform, but the harmonics are now evaluated at the points of the integer lattice. Okay, this is the Fourier series that holds for periodic functions. Okay, so let's compute this Fourier coefficient. Let's take our periodized function and plug it into this inner product. Okay, so this is the inner product I wrote. It looks exactly like the Fourier transform at integer frequency n. Okay, so let me write it like this. I'm writing the periodized version of psi in terms of psi here. Okay, basically this term is what I wrote in parentheses. Okay, I'm substituting a new integration variable x prime equals x minus m. Okay, pay attention that the integral here, the inner product here is on L2 0, 1 to the power d. Obviously, otherwise you get an infinite number. Okay, because the function has infinite energy. It is periodic. So I will change the order of sum and integration. It will be sum over m, integration with respect to x prime, this new variable that I defined. Okay, and I can think of this integral and basically I can split this exponential into something that depends on the integration variable and something that doesn't depend on the integration variable, but it still depends on the summation index m. Okay, and then just remember what is this. This is a harmonic that makes an integer number of periods, right? Because both n and m are integer, right? What is the value of this harmonic? I'm making a full circle starting from 1. I'm returning to 1, right? Because I'm making an integer number of circles, the integer number of periods. So this is just 1, and I can drop it, okay? And what I'm left with is this sum over m of non-overlapping integrals, right? So basically, I'm tiling my space with these integrals of on 0, 1 to the power d, right? So basically, I'm integrating on the entire space Rd by splitting the integral into these small tiles and summing the results together. The tiles are non-overlapping, therefore I can write the sum of the integral in this way. Okay? So it's integral over Rd, and this is nothing but the forward Fourier transform of psi evaluated at point n. This is my Fourier coefficient. Okay? Now, is this surprising? Not at all, right? We can see it immediately from the starting expression. Okay? And let me denote it by capital psi at point n. Capital psi is the Fourier transform of the test function psi, non-necessarily periodic. Okay? So just let's substitute it here. Okay, so we have psi periodized at point x. We expanded into the Fourier series and substitute the expression that we found for the Fourier coefficient. And this is what we get. It will be the sum of these harmonic functions evaluated at point x with frequency n with a coefficient equal to the Fourier transform of psi evaluated at integer frequency n. This is on one side. And on the other side, we have the definition of what it means to periodize psi, right? We periodize it, we simply sum the replicas on the same integer lattice here and here, right? And let's now consider the particular case for x equals 0. Let's substitute the x equals 0 into this identity. So I care, of course, about the identity between this and this. Okay? So on one hand, I have psi minus n summed over n. On the other hand, I have capital psi at n summed over n. So let me just write here n prime and remove the minus sign. Summing over minus n and summing over n over the entire lattice, it's exactly the same thing, right? And then let me remove the prime because it's just a name for a summation index. Okay, so basically what I get is this. Okay, what I get is this. So I have that the sum of the function on the integer lattice is equal to the sum of its Fourier transform on the integer lattice. Okay. Now it's quite incredible, right? It's not a fact about the Fourier transform. It's a fact about the integer lattice itself. So you can write the same thing in two different ways. It is usually a sign that it is something profound. Okay. So we have this. Let's now see, and I will steal 2 minutes from your time, and I would like just to finish here with the consequence, the corollary of this exercise that we did. So I will take the Fourier transform of Dirac's bed and compute the inner product with the test function psi conjugate, right? This is the application of the distribution that is obtained by Fourier transform of the Dirac's bed. I will move the Fourier transform from the distribution to the side of the test function, and I will, of course, take the transpose of this operator, which is f inverse. I had to somewhere the conjugate is missing. So I will obtain this, right? So I'm just denoting the inverse Fourier transform of psi by lowercase psi. Okay, and we know that basically applying this inner product to the test function gives us the periodization of psi, right? Because we are evaluating the summed shifted version of psi at point 0, right? So this is what we are getting from this expression. Okay, from Poisson's identity, this result that we had before, we can also write it as the sum of the Fourier transforms of psi sampled at integer frequencies. Okay, and this will be equal to the Dirac's bed applied to psi, to capital psi conjugate, to the Fourier transform. So somewhere I think I'm missing a conjugate here. So probably you should be writing conjugates every. We'll check it next week, but the result will remain the same. So basically, it means that the Dirac's bed stays the Dirac's bed under the Fourier transform. Okay, so the Fourier transform of of a delta is a constant function 1, but the Fourier transform of a periodized delta, which is Dirac's bed, is a Dirac's bed. Okay, and this is quite a remarkable fact. Why is it remarkable? Because if I now do element-wise product with the Dirac bed in the space domain, it becomes convolution. Of course, product becomes convolution under the Fourier transform. With the Fourier transform of Dirac's bed, we just learned that it is still the Dirac's bed in the Fourier domain. Okay, so element-wise product in the space domain, we identify this with sampling. And the sampling will become periodization of the Fourier transform. Okay? So from here, next week, we will prove a very important theorem that is called the sampling theorem. We will just state conditions under which this periodization doesn't lose any information. And if we don't lose any information, we'll show how immediately we can recover the continuous function back from its samples. Okay, and we'll call this result the sampling theorem. I would like to very briefly remind you what we did last time, and then we'll continue talking about sampling and interpolation. The main object that we constructed last week was the notion of a distribution and the delta distribution in particular. So I hope I was able to explain convincingly that delta is not a function. Okay, so if you think about some space of functions, we know, for example, that we can think of a delta, for example, as a sequence of Gaussians with decreasing variance. So let's say this will be some Gn, okay, sequence of functions. And the functions have unit area under the curve, but decreasing variance. Okay, so you can say that the limit of this sequence, if you, for example, if you integrate Gn with some function, then in the limit this will converge to the value of the function at 0, right? As n goes to infinity. Okay. Or you can say that you have another sequence, for example, of these rectangular functions, also with unit square. Let's call them Hn. So this is one member of the sequence. This is another one. It has a higher and shorter rectangle, again unit square. With this function as well, if you integrate some test function with the Hns, you will get something, and that something will converge in the limit to the value of f at 0. Okay. So you might be tempted to write something like this, like lim gn or lim hn, right? So you can write this, but this object will not be a point in the space of functions. So there is a limit, and the limit point is a hole. So it's not in the space of functions. Okay, it's a different object. It's a different object that is called a distribution. So basically, the space of functions is dense, but it has many holes, and those holes are exactly in order to be able to actually write them as a mathematical object rather than carrying these limits all the time with us. We need to define a bigger space that is called the space of distributions. Okay, so this is how we defined the delta. This is how we defined what we called Dirac's bed, which was a sequence of translated deltas, translated on the integer lattice. Okay, and basically what we did, we studied the property of this Dirac's bed, right? We saw that doing element-wise product, and we defined what it means to do an element-wise product of a function with a distribution, right? We used transposed operators for that. So we saw that multiplying with Dirac's bed gives us sampling, and we saw that doing convolution with Dirac's bed gives us periodization. So we periodize the function on the integer lattice. Okay, and then last thing we did in the last lecture was showing this identity, which is called Poisson's identity, or Poisson's sum. So basically, this identity tells us that if we take any function and sum it on the integer lattice, then the result will be the same as summing its Fourier transform on the integer lattice. Okay, so basically, here I'm taking integer samples, integer locations in the space domain, and here I'm taking integer frequencies in the Fourier domain. Okay, and quite surprisingly, the two sums give exactly the same result. Okay, and this is what we proved last week. Now, if we use this identity, so if we start with this identity, let us see what it gives us in terms of the Fourier transform of Dirac's bed. Okay, so I will take a test function psi, and let me denote it as capital psi, because just by convention in the Fourier domain we use capital letters, but it doesn't matter, it's just a regular test function. And I'm computing the action of this functional, which is the Fourier transform of Dirac's bed on this test function. And remember, we write it as inner product of this functional with psi conjugate. Okay, this was our notation for the action of this linear functional. Okay, and of course I can write it using the conjugate, the adjoint operator of the Fourier transform, which is its inverse. Okay, acting on psi on psi conjugate, and by using Poisson's identity. Sorry, still without using Poisson's identity, I will just denote the inverse Fourier transform of psi capital adjoint conjugate as lowercase psi conjugate. Okay, just a regular notion for the inverse Fourier transform. Okay. Now, what is written here? What is the action of this functional on psi on the test function psi? I'm basically I'm applying shifted deltas to a test function. So every shifted delta will give me the value of the function at a point n on the integer lattice, right? And then I'm summing them up. Okay, so this is going to be the result, right? And you see, it looks like the left-hand side in our Poisson's identity formula, right? Now, I can use the identity formula, what is written here, to rewrite this in terms of the Fourier transform. So it will be identical to summing the Fourier transform on the integer lattice. Okay? And this is, again, the action of the Dirac's bed on psi capital conjugate, on the Fourier transform of psi. Okay? So basically, we write something that resembles what is written here, but now in terms of psi capital. And you see that on one side, so it's the same test function here and here, right? And we have, on one side, we have the Fourier transform of Dirac's bed acting on the test function. On another side, we have the Dirac's bed itself acting on the same test function. And this is, of course, true for every test function, right? So it means that these two distributions are identical. We cannot distinguish between them. Right? So if we could, we cannot. But if we could realize them as functions, of course, this would be just an equivalence class, right? This is what weak form stands for. But basically, we cannot distinguish these two distributions, so we will just say they are identical, right? Because these are two linear functionals. They return the same values for the same inputs. And we can compactly write this by saying that the Dirac's bed is invariant under the Fourier transform, right? So basically, its Fourier transform is Dirac's bed itself. See? And actually, in our definition of the Fourier transform, I on purpose chose a specific definition of the frequency that doesn't include the normalization by 2 pi, exactly to get to this nice formula. Okay, so you could define the Fourier transform differently, but then ugly constants would pop up here. Okay, so I preferred this part to be as aesthetic as possible. Okay, so if we have this identity, so this is how I would like to summarize Poisson's identity, that the Dirac's bed remains invariant under the Fourier transform. Okay. So now, what happens if we do pointwise product with Dirac's bed with some function? So we know that this gives us sampling, right? Sampling on the integer lattice. We are going to take every integer d-dimensional tuple of the coordinates of f and retain the values only there, right? Because the rest of the values will be gone. So we're going to do sampling. Now, in the Fourier transform, we know that product becomes convolution, f becomes the Fourier transform of f, and the Dirac's bed remains Dirac's bed, right? So basically, it will be convolution with Dirac's bed. And what is convolution with Dirac's bed? It's periodization of the Fourier transform. Okay? You see it? So basically, sampling in the Fourier transform becomes periodization. So I will show you a one-dimensional example, then I will show you a few two-dimensional examples. So in one-dimensional example, in the space domain, in the time domain, if you will, we have a continuous function, and then we sample it. Okay, you see we're retaining just the values of the functions here. These are the scales of the shifted deltas that we get in this distribution. Okay? Now, in the Fourier transform, let's assume that we had this Fourier transform of the original function. I'm just drawing it as some arbitrary shape. And what we are going to do, we are going to shift this shape to integer locations. We have just scalar frequency, so it is 1 and -1. Otherwise, it would be the d-dimensional integer lattice. And we are going to sum the result. Okay, and basically this blue curve is the result. It is the periodized Fourier transform, and I can denote it by f tilde. Okay. So basically, sampling results in periodization of the Fourier transform. Okay. Now with this understanding, we can immediately write what is called a sampling theorem. So a sampling theorem, of course, you can say, basically, there is a fundamental question here that we need to answer. So we are taking a continuous signal, and we are just retaining a discrete set of its values, right, at some regular grid. Of course, this is overwhelmingly less information that we had to start with, right? So we have basically we have a continuum of values that we are dropping between every sample. Okay? Can we go back? Can we reconstruct the signal perfectly from that sampling? It's a fundamental question, because basically, if you cannot, then what is the sense of doing digital signal processing? It's nice that we can operate with sampled sequences, but how do we go back? So for example, our camera took an image of this world, we did some manipulation in the digital domain, can we display it back? Can we again produce a continuous image? If we cannot, then basically all this exercise is useless. So basically what many people tried to understand and to rigorously prove is how to, and under which conditions can you go back from the digital domain to the analog domain? Basically, how to reconstruct a function from its samples. Okay, and to define this formalism, let me define what is called the support of a function. So the support of the function is the set where, on which it has non-zero values. Okay, so this is the support of a function, and I will say that the function f is band limited if the support of its Fourier transform falls into this d-dimensional unit square. Okay, so it's a square with unit length centered at the origin, d-dimension. So it's a d-dimensional cube, actually. Okay, and I will call it band limited. Okay, it's the origin of the name goes back to telegraphs and communication on wires, but we'll keep this notion and we'll extend it in a few minutes. Okay, we'll call it band limited. Of course, if we have a one-dimensional signal, then basically it means that there is no frequency content above frequency 1/2 and below frequency minus 1/2, let's say measured in hertz or something like that. Or if we are talking about an image, then basically all the spatial frequency content is contained within this square. A question? Yes, please. Yes, because so the function is band limited. Band limitedness is the property of its Fourier transform. Okay, and of course, because we know that the Fourier transform is a completely symmetric operation, we can instead of saying that something is band limited, we can think about something compactly supported. Okay, so some function is compactly supported in the original, in the primal, in the space domain, and this will imply something about its Fourier transform. For example, that it cannot be compactly supported as well, right? Like the uncertainty principle that we have seen. Okay. So if the function if the function is band limited, then basically what happens under periodization? So if the function is not band limited, periodization will lose information, right? Because there will be overlaps between the replicas of the function when we periodize it on the integer lattice, right? I showed to you this overlap in the previous illustration. I will show you some more concrete examples. Now, if the support is entirely contained in this unit square, unit cube, then periodization destroys no information, right? There will be no overlaps, okay? And otherwise, we'll have a phenomenon that is called the aliasing. So what is aliasing? Aliasing means the following. So as you can see, this is a two-dimensional overlap. This is what is written here. What is denoted here in red is my unit square. And you can see that the Fourier transform, which is denoted here, basically just the support of the Fourier transform is denoted here in white, doesn't fully stay within this red square. Okay, and as a result, when I'm periodizing it on the lattice, there will be overlaps. Basically, these overlaps of the replicas, and what will happen is that this, for example, this high frequency here will be folded back as a low frequency in the periodized Fourier transform. So if I had, for example, in the one-dimensional case, some high tone that is above my sampling frequency, it will appear as some low frequency beating, a very unnice and unpleasant phenomenon. And for example, I will show you next a few examples of aliasing. Okay, so let me first show you the theorem. But anyway, you have certainly seen what is called moire patterns in images. So, for example, if you have some very high frequency irregular structure like a fence or maybe stripes on a shirt, from sufficient distance from the camera, they will appear as stripes with some very smooth low frequency patterns popping up out of nowhere. So there were no such low frequency patterns in the image in the first place, but they appeared as a consequence of aliasing. Okay, so I will show you more examples in a few minutes. Okay, so basically, if periodization destroys no information, how do we go back? So the trivial thing we can do, we can just remove all those periodized replicas by putting a low-pass filter in the frequency domain. So we'll just do a product of the periodized Fourier transform with a box with this filter, right? And all the rest will be gone, because the box has support 0 outside of this unit square, unit cube. Okay, so let's rewrite this in the space domain. So this is what happens in the Fourier domain. In the space domain, this will be the Fourier transform. Should be the inverse Fourier transform, of course. The inverse Fourier transform of the periodized function. Product becomes convolution, and the inverse Fourier transform of a box is a sink. Okay, we defined this already. Sink, because the box is a d-dimensional creature. The sink, of course, will be a tensor product of one-dimensional sinks, and as the box is a tensor product of one-dimensional rectangle functions. Okay, and this, of course, becomes. We know that basically the inverse Fourier transform of this periodized function is just sampling, right? Sampling convolution with sink. Okay, so let's write this expression explicitly for a specific argument x. Okay, so basically on this side I have, on the left hand side I have f. This is f at a particular value of the argument x, and on this side I have the sampled version of the function. This is what is written here: convolution with sink at the same point x. Okay, I should have written it like this probably. Okay, so I'm just substituting. So basically, I can write this as convolution with the delta, right? Basically, or with the translated delta, because Fn is just a scaling. Okay, so the scaling remains. What convolution with shifted delta gives us? So convolution with a shifted delta gives us simply the function shifted by the same amount, right? So I get sink at x minus n. Okay, so basically we have f on the left-hand side, and this sum of scaled and shifted sinks on the right-hand side. So basically what we have is this. Basically, I started with my function, I sampled it at some regular set of discrete samples, and then at every sample I placed a sink. Okay, so every sample here has a different color. And then I summed the contributions of all these sinks, and voila, the magic of the sampling theorem tells us that I'm going to get this orange waveform precisely as it was before. Okay? So basically this identity tells us how actually to reconstruct a signal from the samples. Okay? And this is known as the sampling theorem. In the order of its publication by this respectful gentleman, it should be probably attributed to Kotelnikov, to Whittaker, to Nyquist, Hartley, and Shannon. And I'm sure there are many other people who also discovered or somehow used this theorem in their works. This just, so basically everywhere in science and in engineering, if the same result is discovered multiple times by different people, it means that it is of fundamental importance, right? And this is the case of the sampling theorem. As you can see that once we had this Poisson's identity, the sampling theorem was just a simple geometric consequence of this identity, right? So basically the fundamental fact about sampling in periodization was Poisson's identity. And this is just a simple corollary. Okay, any questions? So this is the promised example of aliasing. So you see we have a regular structure here, this fence. But look what happens here. Do you see this low frequency pattern? Basically these patterns here. This is not part of the structure. This is just an artifact caused by aliasing. Yes, question? Okay, so let me just draw a one-dimensional example. So this is my original Fourier transform. Okay, And let's take this high frequency and suppose I'm not so I'm supposed to sample at sufficiently with sufficient density. So I'm not. So we currently we are talking about some kind of a canonical normalized sampling theorem. So we are saying that the function has to be band limited. Okay. So let's say I'm not changing the sampling rate, the sampling frequency yet. Okay. So we'll get to it. But suppose my function is not exactly band limited. So this is supposed to be the band limit of 1/2 and minus 1/2. Okay. So this is going to be 1. Okay. So I'm not satisfying this condition of being band limited, and this is going to be my replica of the Fourier transform, and this is another one, of course. So if the function is real, we didn't mention this, but the Fourier transform is conjugate symmetric. Okay, so it has the same thing up to opposite phase on both sides of positive and negative frequencies. So basically, you can see that this high frequency here, okay, this is very high frequency. It somehow, basically, it is replicated here, and it became a lower frequency here. Okay, so it depends on how you engineer these overlaps. You can put another higher frequency here that will be almost DC, almost constant. So something very slowly varying. Basically think of some sine function that changes very, very slowly in the space domain or in the time domain. So in the time domain, you will hear it as beating, some very, very, very nasty, slowly varying difference between let's say two tones, something that slowly goes in and out of tune. Right? This is very annoying. For example, any stringed instrument with sufficiently thick strings, like the piano, for example, would produce some amount of beating. That's why the pianos are made with very long strings, as long as possible. And in images, you will see exactly these kind of patterns that are called moire patterns. Okay, so again, this basically slowly varying pattern was not in the original image. It's an artifact of its digitization, of its sampling. Okay, and this is a temporal example of aliasing. Okay, so this is a classical spinning disk with different frequencies, different spatial frequencies. So when you spin it, look what happens. In which direction is it rotating? So it rotates in this direction, right? But how come you see it basically changing direction and then basically also changing speed? So it comes to a stall and then changes the direction of rotation. This is exactly the same aliasing effect, but now happening in time. Okay, so basically this spatial frequency, when it is rotated, it becomes a temporal frequency. So there is some temporal change of white and black values of the pixel, right? And when you sample it in time with a certain frequency, with a certain temporal frequency, it becomes aliased, and you get this frequency with an opposite phase, which means that it rotates backwards at much lower frequency. Then aliasing moves you again basically across all the range of possible frequencies that you might have. Moire? Yes. Okay, so basically, of course, once you have, so you see the fence. This is a typical example. This is how resolution charts are also built for testing imaging systems. So you see here the frequency increases as you go deeper because of the way the projective transformation of the world works. Okay, so basically the same distances between. So the fence has a regular pattern with equal distances between its elements, but when it becomes deeper in the image, it spans a smaller angular span, so it takes less pixels on the image sensor, and the spatial frequency on the image sensor increases as you go basically from the left to the right. Okay, so the frequencies go beyond what is called the Nyquist frequency, the highest frequency at which we can sample without losing information, and then higher frequencies start popping up in lower frequencies as the consequence of aliasing. You always miss the higher frequencies because basically when you reconstruct, the highest frequencies you can get is that frequency 1/2 that we wrote. Okay. So basically, of course, this was a very idealized world. So we are assuming that if the function is band limited, then we are going to get it perfectly back. But nothing in the real world is band limited, especially images. So in images, if you think how an image is formed, an image is formed by light reflecting from a scene, and a scene has objects that end abruptly, and then beneath you have another object. So you have a discontinuity, right? And the discontinuity is something that not only does it have infinite frequencies, so it basically has energy until infinite frequencies, it has the slowest possible decay in the Fourier domain. It decays as 1 over the frequency. So basically it has a lot of energy in very high frequencies. And therefore, if you try to sample an image without any precaution that you're making, you are going to get aliasing. Okay. So what has to be done for real signals is first to remove the high frequencies. This has to be done in the analog domain. It has to be an analog filter. So it means an electronic circuit for time sequences, for time signals, let's say audio, or some optical system for images, right? So we are going to apply a low-pass filter that will attenuate or ideally completely remove frequencies higher than 1/2 that we are required to obey according to the sampling theorem. And of course, this filtering can be written as convolution. Okay, so here we are still in the analog domain, and then we are going to sample. Okay, so we convolve with this low-pass filter, and as you have seen in the exercise, basically low-pass filtering, something that removes high frequencies, will make the image appear blurred. So those sharp edges that we had in the image will become less sharp because the high frequencies are attenuated or removed, and basically the image will appear blurred. So now, if you look at the algebra, so you have the convolution of f now being sampled by a pointwise product with the Dirac's bed. So let's write this convolution explicitly here. This integral inside the sum is exactly the convolution integral, right? And I'm evaluating the convolution at the point n. Okay, so let's now see what happened here. So basically, we are integrating the function with some window h, and we are taking its value at the sample n, at the location n. Okay, so we are not basically what happened here. If we do idealized sampling, we are just taking the values of the function and measuring their pointwise values at some point. This is what the deltas did. What we are saying that we are first going to do anti-aliasing filtering of the function. We are going to blur it with some window h, with some filter h, and then we are going to do this idealized sampling. And you can see that equivalently, this can be thought of as, instead of taking pointwise values, we are going to integrate the signal with the shape of the window h at the same location. So if this was idealized sampling, this is real sampling with a window like this. So it's not exactly a delta. It's a window that has a certain spatial extent. Okay? And we are going to integrate the signal with that window. It can be in time, it can be in space. Okay? And basically, so you are never sampling with a delta. So for example, if you are sampling an image with a delta has no, it occupies no area. How can you collect photons with something that occupies no area? You need a bucket that will be filled by the flow of light that falls onto the image sensor. So you need this bucket to have some aperture, right? And basically in real optical systems, of course, the effect of anti-aliasing is done exactly by shaping this integration window in the real sensor array. Okay. Okay, so in case of sampling temporal signals, and let's say I'm talking about basically about imaging systems. So basically, when we are taking a video sequence, the integration in time is done by an electronic shutter that tells the pixels now start integrating and then tells now stop integrating. Okay, so basically there is a certain window in time that is called integration time or exposure time when the pixels accumulate photons and convert them into electrical charges. In the spatial domain, we have each pixel has a certain spatial integration pattern. So it has, first of all, some light-sensitive area. I will show you next time how the sensor looks like under a microscope. So it has a certain area that is sensitive to light. And then above this wafer, there is also a micro lens that collects light into that area. So basically, all these effects combined define some spatial window in which an individual pixel collects light. Okay, and of course the reality is much more complicated than this because it also depends on which angle the rays come at, and there is some crosstalk between the pixels. But anyway, this is at least a simplified situation. And then we also have the optics of the imaging system itself, the lens, that also has some low-pass properties, right? For example, if the lens is not exactly at focus, it will be acting as a blur, as a low-pass filter. And optics people use this term as MTF, modulation transfer function, to define how the lens passes different spatial frequencies. And even if the lens is perfectly in focus, it is limited by what is called the diffraction limit, and which depends on the wavelength of the light. But basically, you cannot have resolution. You cannot resolve between details that are much smaller than the wavelength of the light that you are using. Okay, so this is a physical limitation. Now let's have a closer look at how sampling occurs in real devices, in real optical systems. So first of all, when you take a camera like this, how the heck do we get color images from it? So a pixel in CMOS process is sensitive basically to a very wide range of wavelengths, starting more or less from violet, the shortest wavelengths, up to near infrared, about 900 or 1,000 nanometers. So how do we get? So we integrate over all wavelengths. So they respond quite well to all wavelengths. How do we get different colors? Okay, so basically, so how the eye does this? So the eye has an array of 3 types of sensors. One integrates something that resembles red colors, at least long wavelengths. Another one that integrates quite a wide range of intermediate colors, something that picks at green. And another one that integrates a little bit of red and a lot of short wavelengths, which is called blue. Okay, so this is how the eye does it. Now, in real cameras, we can of course put 3 sensors, a complicated optical system, and this is how, for example, all the high-end cameras for astronomy are made. But in consumer devices, this is not how cameras work. There is only one sensor, one array of pixels, a much simpler optical system, and then each pixel is colored with a filter. So the filter is painted on top of each pixel. And this is called the CFA color filter array or Bayer mosaic. Okay, so basically we are imposing an array of color filters on top of an otherwise panchromatic array of pixels. They are sensitive to all wavelengths. And this is how it looks like. This is the typical Bayer mosaic. We sample twice more green than blue and red. So this is called the subpixel geometry. This is the repeating pattern that we are tiling over the entire area of the sensor. Okay, so if you take the green in particular, this doesn't look like sampling on a regular grid, or I mean it's a regular grid, but it's not a Cartesian grid, right? You see, it's not a matrix. You don't get a matrix here. The rows, every even row and every odd row are shifted with respect to each other, right? So you can think of as sampling on this particularly distorted lattice, okay, that I drew here with these 2 red arrows. Well, but it's not orthogonal. The angle here is not 90 degrees. Okay, you are never going to get a matrix out of here. Yes, a question? Well, of course, different colors have basically, they have different sampling frequencies, right? So the sampling frequency is not exactly something that is helpful here because different directions are sampled at with different step lengths, right? But I would like to use this formalism of lattices to talk about general forms of sampling. Okay, but just pay attention. This is real life. This is how 99.9 cameras are built. This is the sampling, not a matrix. Yes. Well, there are, you can think of it this way, but basically you want. So the truth is that in natural images, the sharpness, the edge information is contained in all chromatic channels. This is how it works, because these are edges of boundaries of objects, right? So you want one of the channels that you are sampling to contain as high frequencies as possible. Okay, so if you have something sharp, then coloring it will be easy. So the human visual system is very sensitive to loss of sharpness, and it is much more forgiving to not coloring exactly correctly that sharp image. So the idea here is that you take an achromatic image at the highest resolution you can, which conventionally is done by sampling green, and green is not monochromatic. It's a very wide spectrum response, so it samples all colors more or less with double the resolution, and then you sample the colors with some sacrifice of spatial resolution, and you color that sharp achromatic channel with these two additional color channels. So you want somewhere the highest frequencies to be contained. And conventionally, this is done in the green channel. This is what our eye also responds to with the highest response. Well, because basically, at least in the natural environments in sunlight, this is where the peak of the black body radiation coming from the sun also peaks. So that's why our eyes also evolved to have the highest response about this magic number of 555 nanometers, something like that. Okay, so again, this is spatial frequency in the vast majority of image sensors. Now, if you have a closer look at how videos are taken in cameras, so for example, if you take this camera, the majority of cameras that you will find, at least for consumer products, use what is called rolling shutter. Okay, so rolling shutter. And there are basically design issues that pixels with rolling shutter are easier to manufacture. They have slightly better SNR, and the rolling shutter means simply that the integration time, that time where the pixel starts responding to light and then stops responding to light, basically starts collecting photons and stops collecting photons, that interval is slightly staged with small delay for every consequent row in the sensor. So the first row gets integrated, let's say, starts integration. The length of the integration interval is exactly the same for every row, but the starting time of the integration is shifted as you go down in the rows of the sensor. So if you look at it in this spatio-temporal cube that I tried to depict here, you see that basically you're again going to get some kind of a non-orthogonal lattice. Okay, basically non-orthogonality because of this staging of the integration of the rows. Okay, so now if you want to get a video out of it, you somehow need, if you want to show it as a matrix, because you usually displays usually display all the pixels at the same time in a single frame. So you somehow need to resample it to that device, right? But we are still not talking about resampling. We are going to talk about it next week. This is just to show that there is a real need, basically real devices. Most of the devices that you will find will actually do this kind of spatial-temporal sampling. And again, combine this with the Bayer mosaic, you also have some non-orthogonal lattice in the space domain. So basically, we need some formalism to define sampling on these non-Cartesian creatures, right? Another example that is more or less obsolete nowadays, but previously the cameras that were used, analog cameras mostly, were using what is called interlaced scan. And interlaced scan means that you don't really take all the rows of the frame at the same time. You integrate the even rows instantaneously at one time, and it is called the even field of the frame, and then half the frame integration time afterwards you integrate the missing rows. And if you for example take DVD, which is by the definition of the standard is interlaced video, you can see that when there is fast motion in the movie, there are some kind of saw teeth artifacts on the boundaries of objects. This is exactly the interlacing that the content was produced with. Okay, and again, interlacing results in some non-orthogonal sampling of the spacetime. Okay, yes. Well, so there are many historical reasons. So basically, this starts with CCD devices that had simply electrical obstacles in getting all the rows integrated and read out simultaneously. So basically, it depends on the device, but this somehow, I think, TV standard moved to progressive scan something like 10 years ago, maybe slightly more. So it actually was with us for many decades. And now you still have a lot of content that was acquired using interlaced scan. So there is a need. Actually, what the TV will do, which is TVs, basically modern TVs like OLED TVs, are progressive. Progressive means the opposite of interlace. That all the rows are displayed simultaneously. So it will do some image processing in the digital domain to do this conversion, right? So we'll see how exactly this is done. Yes, a question? The progressive scan is, well, so the rolling shutter is not exactly a progressive scan, but progressive scan is a scan with a global shutter when you have all the lines of the frame integrated simultaneously. Well, of course. So here I'm talking about sampling, but when you interpolate, you also interpolate using some device capabilities, right? Okay, so let's define the mathematical tool that will allow us to be able to express the action of these real sampling devices. And for that, we are going to define the notion of a lattice. Okay, so we started with the integer lattice. We did all our sampling so far on the integer lattice, and this resulted in some canonical unit cube that we had in the Fourier domain, where the function had to be band limited. Okay, so let's take our lattice and define a general lattice as a linear transformation of the integer lattice. So I will take a regular D by D matrix A, and I will scale the elements of the lattice by this matrix A. Okay, so when I write A times ZD, I actually mean that I take n from ZD, so it's a tuple with integer coordinates, with D integer coordinates, and then I take n one times the row, the first column of A1, then I add to it n2 times the second column of A, so on until I add to it nd times the last column of A. Okay, so and this will define the general lattice. I will show you a picture in a second. And then I will define what is called the structural element of the lattice. So the structural element of the lattice is the smallest set so lattice gives us just integer points, right? So if I define a tile and I replicate this tile over the integer elements of the lattice, what is the smallest set that will cover the entire continuous domain? And this smallest set is called the structural element. Of course, it is defined up to any shift, up to any translation. So I will canonically say that the structural element of the integer lattice is this d-dimensional unit cube, right? So if you take the union of all the replicas of all the translations of this unit cube, you will get exactly RD, okay? And in the case of the general lattice, I will denote by L0 the structural element of the lattice. It will be just the same linear transformation A acting on the unit cube, okay? And the volume So I will say the volume of the lattice, actually referring to the volume of the structural element. What is the volume of the structural element of the integer lattice? It's 1, right? It's a unit cube. It has unit volume. So in this case of a general lattice, what would be the volume of the general structural element? It will be the absolute value of the determinant of A, right? This is the meaning of the determinant. It scales volume forms by basically. This is what we also used when we changed integration variables for the same reason. Okay? And this is how it looks like. So I start with the integer lattice on the left, in this case Z2. E1 and E2, the two standard Euclidean basis vectors, are its generators, right? And I'm just taking integer coordinates in this basis, right? And this gives me the points of the lattice. And the red square is exactly our structural element of the integer lattice. Okay. Now I'm applying linear transformation A, and what happens? E1 is transformed to A1, right? This is A1, and E2 transforms to A2. The unit square becomes a parallelogram with volume determined by the determinant of A, right? And of course, for example, when I traveled to this point, which was given by the tuple 2, 1, now I will travel to it here, okay? So it will be twice the vector A1 plus once the vector A2, okay? So you see how this is constructed, and you can see that all our cases that we have seen, the bare mosaic, the rolling shutter, the interlaced sampling, we can take care of all of them using these formulas. Okay? So let's now generalize our sampling theorem to the case of general lattices. Okay? So again, remember that our tool for defining sampling was the Dirac's bed. So when we multiplied with the Dirac's bed, this was sampling. Then we observed what happens in the Fourier domain. That was periodization. And from trivial geometric reasons, we could define the conditions under which we get perfect reconstruction and how exactly to get the perfect reconstruction by applying an ideal low-pass filter in the frequency domain. Okay, so let's now define the Dirac's bed on a lattice, on a general lattice, and we'll see what happens in the Fourier domain, and we'll define a generalized sampling theorem. Okay, so this is the purpose of this exercise. So I start with lattice L, defined by the matrix A, and I define the Dirac's bed with the subscript L by simply taking shifted deltas, translated deltas, on the lattice L rather than on the integer lattice. Okay? And I can, of course, write the sum going still over ZD, and I will have P equals to AN. Okay? So I can parameterize every point in L in this form. Okay, so let's do a small side exercise. And so I know what is the end result, so just bear with me. So I would like to express the translation of f at point x by this amount, by this amount p, which I write as an. Okay, so this will amount to fx minus an, right? This is how translation is defined. Okay, so let's add another operator. This is not what I wanted to show you. Anyway. Okay, so I do this exercise. I had a better way to show it to you. Okay, let's do the break, and I will show you it in a better way. Okay, so basically, I'm defining a Dirac's bed. So Dirac's bed was a periodized delta. So it's a sum of translated delta on the integer lattice. Now I would like to extend this to a general lattice. So I'm simply summing the shifted deltas over the elements of the generalized lattice, which is defined with the matrix A. Okay, so let's do a side exercise. I fix this now. So I'm taking my function f, and I would like to stretch its coordinate by the matrix A. Okay, and when I evaluate the result at point x, it is equivalent to substituting ax to the argument of f. Okay, then let me translate this by the amount n. Okay, so I'm adding another operator from the left. It means that I first stretch, then translate, and translation means that instead of x, I substitute x minus n. Okay, and then let me stretch the result by A inverse. Okay, so stretching by A inverse, it means that I substitute A inverse x to the previous result. Okay, so let's now open the parentheses in this expression, and what we get is fx minus an. Okay, and fx minus an is exactly f translated by the amount an evaluated at x. Okay, so this, of course, is valid for every f, and it would be valid for every distribution as well, right? So now we know that this sequence of operators is equivalent to this. Okay, but what is written on the right-hand side is what I have in my expression in the first place. So let's write it like this. It will be so basically this operator is replaced by what I wrote here. Okay, and it acts on the delta distribution now instead of acting on the function f, but it's the same operator. Okay, so I can write it like this. I will use the fact that SA acting on delta. So what does it mean to stretch the delta? The delta remains the same distribution, just the scaling by the determinant of A pops up in the end result. So this is the scaling. Okay. Then I have translation by tau n, which remains. It's translated delta, and I will move this stretching by the inverse A outside of the sum. Okay. All these are linear operators, of course. Okay. So let me write it in a different way. It will be stretching by inverse A over the absolute value of the determinant of A. And what I have here is nothing but Dirac's bed, right? The canonical Dirac's bed on the integer lattice. So basically, it means that I can define my generalized Dirac's bed on the lattice L as the stretching and scaling by the volume of L. I'm using this notation here, and stretching by A inverse of the canonical Dirac's bed. Okay, and it will be useful. Why is it useful? Because now, when I write it in this form, I can immediately tell you what is going to be the Fourier transform, right? Because I know how these operators change under the Fourier transform. Okay, so let's compute the Fourier transform. The Fourier transform of this generalized Dirac's bed. Okay, so we have this stretching property, right? That stretching becomes stretching by A inverse transpose. We call this the reciprocal matrix. We also denoted it by A star. So I apologize for loading too much or too many distinct meanings to the star. So star means complex conjugate. For operators, it means adjoint operators. And here I'm also denoting the inverse of the transpose as A star. But anyway, hopefully it is clear from the context that this is not the complex conjugate of A, because A is a real matrix, obviously. Okay. So we have this stretching property for the Fourier transform. So let's now just apply it to what is written here, right? So the generalized Dirac's bed, which is just the scaling and the stretching of the canonical Dirac's bed, will undergo the following transformation in the Fourier domain. So it will become what is written here, this operator acting on the canonical Fourier. Thanks. It will act on the Fourier transform of the Dirac's bed, which we know is the Dirac's bed itself. Okay. Pay attention that because we started with A inverse here, A inverse transpose is just A transpose. Okay. And I can write this as SA transpose of Dirac's bed because the volume of L is the absolute value of the determinant of A, and this is also the absolute value of the determinant of A. Now I wrote times the determinant of A, not 1 over the determinant of A, because I had A inverse in the stretching operator. Okay, so it's the inverse of the determinant. Okay, so let me write now this operator in a slightly funny way. Okay, so let me write it like this. Sorry. Well, let's keep it this way. So basically, I'm stretching the Dirac's bed in the Fourier domain by A transpose. Okay. Now I would like to define what is called the reciprocal or the dual lattice that I will denote by L, guess what, star, which will be A inverse transpose times ZD, or A star times ZD. So A star is again a shortcut for A minus T, A inverse transpose. Okay, so this is the reciprocal lattice. What is the volume of the reciprocal lattice? It is defined as the volume of the structural element. Obviously, it's the determinant of A star, and A star, of course, the transpose doesn't change the determinant, but the inverse does, right? So it's 1 over the determinant of A, which is the inverse of the volume of L. Okay, so at least the volume of these two lattices has a reciprocal relation, right? So one is the reciprocal of the other. Okay, so what is this SA transpose exactly? So let's write it. We know this definition, right? We need some inverse and some scaling to define. It should be this Dirac's bed here, obviously, right? We need some inverse of the matrix A and some scaling by the volume to basically to write this as the Dirac's bed on some lattice, right? So let's see which lattice this Dirac's bed is on. Okay. So let's write it like this. It is S A star inverse. Okay, so what is written here is A star inverse, right? Acting on the Dirac's bed. I will divide by the volume of L star and multiply by the volume of L star. Okay, and what is written here? What is this exactly? It's the Dirac's bed on L star. Okay, scaled by the volume of L star. Okay, so basically we can summarize this property by saying that the Dirac's bed on a general lattice L does not stay invariant under the Fourier transform anymore. It is transformed up to the scale by the volume of the dual lattice to the Dirac's bed on the dual lattice. And apparently the integer lattice is self-dual and has a unit volume. That's why both the scale and the star disappear in this identity. Okay, questions? So if we have this property of the Fourier transform of the generalized Dirac's bed, we can easily see what happens when we sample with it. So if we sample on L, it is equivalent to scaling. Of course, this scaling will always appear. It is equivalent to scaling and periodizing on the dual lattice. Okay, or we can of course swap the roles. We can sample on L star and periodize on L. Okay, and I will prefer this notation. Okay, so I will need to periodize on L, and of course I will have replicas popping up on L because of the periodization, and then I can define what it means to be band limited. Band limited, I will have to stay within the structural element of L. For the support of the Fourier transform of F has to stay within the structural element of L in order to be perfectly reconstructible, right? So it's quite obvious. So what is the reciprocal lattice? Let's define the primal lattice L, defined by the matrix A, and the dual lattice, or the reciprocal lattice, which is defined by the matrix A star. Okay. Now the vectors forming the primal lattice are A1 to AD, the columns of the matrix A. The vectors forming the dual lattice are the vectors A1 star to D star, the column vectors of A star. And what is particular that they form a biorthonormal basis to A. What it means that the the aj star is orthogonal to every ai except that aj, right? So I will show you a picture depicting that. Okay, so they basically form what is called the bi-orthonormal pair, and the volume of the primal lattice is determined by the determinant of A. The volume of the dual lattice, as we said, it's the reciprocal of this volume. Okay, the structural element here is A scaling the canonical unit cube, and the structural element here will be, of course, A star scaling the canonical unit cube. Okay. So this is the primal lattice on the left. It has two vectors, A1 and A2, that generate the lattice. The structural element shaded here in red. Okay. And the dual lattice, pay attention, I have two vectors, A1 star and A2 star. What is particular about A1 star that it is orthonormal to should be the other way. It should be A2 and A1 here. It is orthonormal to A1, and this one is orthonormal here. Is it? No, I think it was okay before, right? Okay. So anyway, you have these orthogonal relations between the vectors of the lattice. This is the structural element shaded in blue, and its area is reciprocal to the area of the red structural element. Okay, so this is the reciprocal lattice, and when we are sampling on the lattice L star, it is equivalent to periodizing on the lattice L, as you can see here. So if we have the Fourier transform not exactly fitting into the structural element, we'll have aliasing, right? Basically, all these overlaps here are aliasing. And if we do fit into the structural element, then we have no aliasing, and consequently we can achieve perfect reconstruction, right? So let's generalize the sampling theorem to these general lattices. So I will start with the lattice L, defined by the regular matrix A, and I will say that F is L0 band limited if its support falls into the structural element L0 of that lattice. Okay. Basically, it falls into this scaled unit cube. So let me now define. So I have a sampling theorem for sampling on the integer lattice and for functions being band limited in the canonical unit cube. So I would like to take advantage of that theorem. I will just scale my coordinates to define a new function g that I will show to you that is band limited on that canonical cube. Okay, so I define g as f of bx, and b will be the inverse transpose of a, or a star, if you will. Okay, so I define this new function g, and what happens to the Fourier transform of g? So the Fourier transform of g up to some scale will be scaled by, the argument will be scaled by b inverse transpose, right? This is the stretching property of the Fourier transform. And b inverse t, what is b inverse t? B inverse transpose is A, right? So what we have here is the determinant of A scaling the Fourier transform of F at frequency AXI. Okay? Now, what about the support of G? So the support of G is the set of all xi's such that it has to be F AXI distinct from 0. Okay? So let's change the variable. Let's denote this as xi prime. Okay. So instead of writing psi, I will write A inverse psi prime, and instead of writing A psi, I will write psi prime, and this is the support. Okay. This is the support. But basically, I can take the A inverse outside this set and define this as A inverse times the set of psi primes, such that F psi prime is distinct from 0, which is nothing but the support of F. Okay, we know that the support of F was contained in the canonical cube, right? So F is L0 band limited. Okay, F is L0 band limited, and now I define a new function. So this support So this support here falls into A times the d-dimensional cube, right? So if I scale it by A inverse, it will be, so the support of G will fall into the canonical cube, right? So G will be band limited on the standard integer lattice, okay? And F is some arbitrary function that is band limited on L0, okay? So if G is band limited on the standard integer lattice, I can reconstruct it from its samples using this cardinal series that we wrote before, okay? This series of scaled and shifted sinks, okay? This we know from the canonical version of the sampling theorem, right? So I write Gx on the left-hand side as Fbx, okay? And let's just, again, remember that B is A inverse transpose, and let's just rewrite this sum in terms of F rather than in terms of G, okay? So I will call Bx Y, and then let's rewrite this sink. Instead of X, I will write B inverse Y, and let's write the sum. Okay, so it's B inverse Y minus Bn, okay? I write it like this. And instead of writing Gn, I will write G B inverse P, where P comes from B scaling ZD, okay? So just some algebraic manipulations, and instead of writing B scaling ZD, I will write P coming from the dual lattice L star. So I'm sampling on the dual lattice on L star. Instead of writing B inverse G at B inverse P, I will write FP. Okay, this is the relation between G and P. And here I will write this sink in terms of the matrix. Instead of B inverse, I will write A transpose. Okay, so you see, we started with a function F that was L0 band limited. So F is L0 band limited. Okay, and we see that we can perfectly reconstruct it from samples on the reciprocal lattice L star. Okay, and the reconstruction is done using these sinks. Okay, so you can think of this identity as the generalization of the sampling theorem. So if you have an L0 band limited function, it can be perfectly reconstructed from its samples on the reciprocal lattice. Okay. So the canonical version of the theorem that we proved before was just for the case that L was equal to ZD, and obviously L star was also equal to the ZD because it is self-dual. Okay. So this is our general form of the sampling theorem. It means that if you want to retain, to be able to perfectly reconstruct functions with high frequencies, you need to sample with higher density, right? Because the lattices are reciprocal. If you have some very long vector in L, it will become a very short vector in L star. Okay, and if you want some particularly high frequency in one direction, that direction, the density in that direction in the other domain has to increase. Okay, so frequency is reciprocal to sampling density. But unlike the one-dimensional case, here we also have this play of non-orthogonal directions of the lattice. Okay, so if F is not band limited, then we will do anti-aliasing, and the ideal anti-aliasing that we will have would be a box on L0, obviously, right? It will be, we'll just take the box and scale it on scale it by A inverse, right? To get the box supported on L0. And if I do the inverse Fourier transform of this scaled box by using the stretching property, it will be sink stretched by A transpose and scaled by the volume of the lattice L. Okay, this is just the stretching property of the Fourier transform. Okay, and this is exactly the sink that appears here. Okay, and obviously you see why, right? Because we obtained this perfect reconstruction by applying an ideal low-pass filter. Okay, so let's look at this transition. So basically, what we have here what we have here is a digital signal, right? It's a discrete domain. It's a discrete domain signal. What we have here is a continuous domain signal, right? So basically it is going from digital to analog. Sampling was going from analog to digital, and here we are going to fill between the samples of the function, right? So our input is this, and we would like to interpolate between the samples, right? So what is written here is an interpolation formula. Okay? So let me write it in a different way. I will write the sum over the integer lattice. Instead of writing p, I will write a star n, right? Because we are interpolating on the reciprocal lattice. And I will just write sinc a transpose x minus n. Okay? And this sinc, so look at this sinc. Look at this sinc ax minus n. So it's a d-dimensional sinc, which we know is defined as the product of one-dimensional sinks, right? And sinc is sine over x, right? So basically, you can write this sinc as a tensor product of these one-dimensional sinks. And what we have in these one-dimensional sinks are the inner products of the columns of A, right? Basically, A transpose X is computing the inner products of X with the columns of A, shifted by the coordinates of N. Okay? Now, again, if I have a 1D sinc, 1D sinc looks like this. And 1D sinc, it is sine, so sinc X equals sine pi x over pi x. Okay? And it is defined to be 1 at 0, because this is just a singularity that can be removed. It assumes the value of 1 at 0, and then it has 0 crossings at all the integers except the 0, of course, right? So basically it has 0 crossings at z minus 0, and at 0 it is 1. This is the one-dimensional sinc. Okay? Each of these terms. Okay? So basically it means that if we now take this d-dimensional sinc on the dual lattice L star, so if I take p from the dual lattice, it is equivalent to taking some vector m from the standard integer lattice and scaling it by a star, right? Stretching it by a star. Okay? So basically, if I write this expression for the sinc, this is p, right? It will give me sinc m minus n. So I'm evaluating this expression at the points of the dual lattice L star. Okay, so I'm substituting p instead of x. Okay, so it gives me sinc m minus n, which of course decomposes into this tensor product of one-dimensional sinks, and this will give me the value of 1 if all the arguments of these sinks are zeros, right? Because I need all the sinks to be 1 in order to get the value of 1. Okay, and this will happen only if all the coordinates of m are equal to all the coordinates of n. Okay, so it means that basically m equals n. Otherwise, if I'm so basically m and n are integers, right? So if any of these coordinates are not equal, it means that one of these one-dimensional sinks will have a 0 crossing, right? Because it will be on a non-zero integer value of the argument, right? So one of these sinks will vanish, and then all the product will vanish. So it means that outside of m equals n, I will necessarily have 0 for this sink. Okay. So pay attention. What we are doing with this kernel, we are scaling it by the value of the sample, and then summing all these shifted sinks, right? So we are sampling the sink by the value of the sample, and then for every, basically, it has some values between the samples, but for every location of the lattice, which is not the sample where I'm standing, the sink, this basically stretched and shifted sink, will assume the value of 0 exactly. So it means that when I sum all of them, the function, the interpolated function, will pass precisely through the samples that I collected. Okay, so basically, here is an illustration. This white waveform is a one-dimensional function, one-dimensional signal. Then I sampled it at these points. Okay, these points. Then what I did, basically what this formula tells me to do, is to take a sink, let's say this blue sink, scale it by the height of the sample, center it at the value of the sample, and just draw the plot. Okay, so you see the plot it takes the values of 0 for every location of every other sample except this one. Okay, then I take another sink, will center it at a different sample and scale it by the value of this sample. When I sum up, at the value of the particular sample, only my sink contributes. The others have 0 crossings. Okay. Well, it's not an indicator. It's called an interpolation kernel. This is what the term interpolation means. So I'm completing the values of the function between the samples, but at the samples themselves, I should better get exactly the same value that I sampled. Okay. So basically, the sum is supposed to sum to this white curve, which passes exactly through the samples. Okay. And this is the property that this thing satisfies. So it's a true interpolation kernel. Okay. Now, the problem with this sink, we are now doing a theoretical exercise, but this sink has an infinite support. Can you do it in optics? Can you do it in electronics? No. Can you design an optical system that has an infinite impulse response and infinite support? This is impossible, right? So we cannot actually build in a real system such an interpolation kernel. So we know that we can reconstruct, or we could reconstruct our function from its discrete samples if we could implement things in real systems, but we cannot. Okay, so the next best thing that we can do is to replace this thing by some other interpolation kernel that I will denote here by P, and try to see what is the damage. Okay, so P is an interpolation kernel, and of course it has to satisfy those properties that we demanded from the sink. So it has to be 1 at the vector 0. And it has to be 0 for all other points on the integer lattice except the 0. Okay, and then when we do this sum, we are going to get the values of the function exactly coinciding with the sampled values at the location of the samples. Okay, is this clear? And so basically, we can of course be completely crazy here. But a very convenient form for interpolation kernels is a separable form. So the sink was of a separable form. We could write it as a tensor product of one-dimensional interpolation kernels. So I will abuse this letter P, and I will still write P as a one-dimensional function. So again, we demand that P0 is 1, and P at every other integer except the 0 is 0. Okay, so it has 0 crossings at integer points except the 0. And of course, if we use such one-dimensional interpolation kernel, make a d-dimensional tensor product out of it, we will get a d-dimensional interpolation kernel that is valid and satisfies these conditions. Okay, and the sink was just one of the examples. Okay, so let's do some theoretical exercise. Okay, so the easiest thing we can do is a 0th order interpolator. So it will be just a rectangle, a canonical rect function that has support on the unit interval between -½ and ½, and it assumes there the value of 1. Okay. Now, if we take samples that are indicated here in white, and we place this rectangular function around every sample, what we are getting is 0th order interpolation. So it means that we don't know anything about the slope of the function. We just maintain the value that we sampled around that sample. And another name for this interpolation is called nearest neighbor interpolation, because when I'm to evaluate the value of the signal, the continuous domain signal here, somewhere between the sample, I will look what is my closest neighbor. I will find this sample here, and I will simply retain its value. Okay. Now, when you do interpolation for time signals, usually causality becomes an issue. So then, if you want a causal interpolation, so if you now think of this axis as a time axis, in order to do nearest neighbor interpolation, you should be able to get backwards in time, right? And also to go to the future, right? Depends on which side of the sample you are standing. So in order to avoid this kind of time travel, what you do, you just shift the interpolation kernel from 0 to 1 instead of being from -half and half, and the interpolation would look like this. So this is a causal interpolation, and it is called zero-order hold rather than nearest neighbor interpolation. Okay, but it's exactly the same. If we go to first order, you can construct what is called a linear, or in the d-dimensional case, a multilinear interpolation kernel, bilinear in case of two-dimensional images, which is simply defined as this rectangular window between -1 and 1. And if you take now the same samples, you place a rectangular window around every such sample, and you sum the windows, what you get is simply equivalent to connecting straight lines between the samples. And arguably, this is what linear interpolation means, right? You can increase the order. The next thing that is used is a third order or multi-cubic interpolation. So here is a cubic interpolant, but if you take the tensor product of these one-dimensional functions d times, you are going to get a multi-cubic interpolation. This is how the interpolation kernel looks like. Another typical choice, and by the way, the third order interpolation is C2. It is continuously differentiable 2 times. So if you want smooth functions to come out of the interpolation, this is the right choice, because, for example, this function is not smooth. It is not differentiable at these points. Okay. Another popular choice is what is called the Lanczos kernel, which is sinc. So the problem with sinc that it has infinite support. So let's just take this sinc, attenuated by another scaled sinc, and crop it outside the window of a certain support. Okay, and this is what Lanczos kernel is doing, and it has nice properties in the frequency domain that I'm not going to elaborate on. Essentially, we are going to encounter these interpolation kernels when we are going to talk about manipulations in the digital domain. So when I, for example, take a sampled signal on some lattice and I want to transfer it on a different lattice, for example, I would like to change the resolution of an image, or for example, I would like to take a rolling shutter image and resample it on some Cartesian grid, I will necessarily have to define sampling and interpolation operators in the digital domain. And this is what is going to occupy our attention next. Then I can choose an interpolation kernel at my discretion, right? Now remember that when we talking about interpolation in the sense of going from the digital domain to the analog domain, this interpolation kernel has to be done in analog hardware. Okay, so it has to be a circuit. If you are, for example, doing audio signals, so some set of capacitors and resistors and maybe, I don't know, amplifiers, something like that. Or it has to be an optical system, right? And I bet you cannot build this kernel in an optical system. Definitely not with something that has negative responses, right? Because you cannot have negative intensities at least in incoherent light systems. This is simply impossible. And this is how real interpolators look like. So basically, sampling happens in cameras, in imaging sensors. Interpolation happens in displays, obviously, or in printers. So this is how the interpolation kernels of real pixels look like. You see, basically, this is a single pixel. It has 3 different colors. Usually, 3 colors are used. Sometimes 4 colors are used. And this is the spatial support of the pixel. So basically, this is an interpolation kernel. Very different from what we would ideally like to see. But this is something that you can actually build. Okay? And you have to live with this. And you can if you really want to do a good job, you need to characterize this very well and do your sampling and do your processing, knowing that this is how you are going to reconstruct the signal, right? For example, you would like to do some kind of filtering in order for all the distortions that this interpolation kernel is going to introduce to be attenuated as much as possible. Okay, this is from the competitor side. Okay, you can see that the density might increase, but this is what is called the subpixel geometry, because these arrays of colored LEDs, in this case, or organic LEDs, form a single pixel, right? Basically, you see that the grid on which we are interpolating, for example, the reds, is not orthogonal in the display as well as in the sensor. Okay, so that was not just a theoretical exercise that we wanted to occupy ourselves with these general lattices. This is actually how reality works. Okay.